So now let us solve the problems on Cauchy's theorem and Cauchy's integral formula. Now let us see the working procedure, that is the steps involved in solving the problems. So first we have to find out the point z equals a, whether it lies inside the circle or outside the circle C. That is the first point. First point is we have to check whether the point z equals a lies inside the circle or outside the circle C. Second point, if z equals a lies inside the circle C, then obviously z equals a is a singular point. So by Cauchy's integral formula, integral f of z by z minus a dz equals 2 pi I into f of a, and integral f of z by z minus a whole power n plus 1 dz is 2 pi I by n factorial into fn of a, where fn of a stands for nth derivative of f of a. So z equals a is a singular point means when you put z equals a minus a becomes 0. That is, this term f of z by z minus a becomes infinite. So z equals a is a singular point. So if z equals a lies outside the circle C, then z equals a is not a singular point. So integral f of z by z minus a dz is equals 0 by Cauchy's theorem. Then one more point you have to remember here while solving the problem. So any fraction which is of the form integral f of z by z minus a into z minus b dz over a closed curve C is equal to, so you have to observe that in the denominator there are two linear factors, z minus a and z minus b. The power of z minus a is 1 and the power of z minus b is also 1. So we can split this fraction as integral f of z by z minus a whole divided by z minus b into dz plus integral f of z by z minus b whole divided by z minus a into dz. So here the left hand side is equal to right hand side. So while solving the problem you have to see this procedure. Now there is one more basic point required to solve the problems, that is a singular point. So the singular point is a point at which the function f of z of a complex variable z is not analytic, or we can also say that at this point, at the singular point, the function f of z becomes infinite, or it is not defined, or we can also say that f of z doesn't exist at that point. So now let us understand this by taking some of the examples. So for example, so if you take f of z equals 1 by z minus 1, so if you see the denominator, it is a linear factor, there is a linear factor z minus 1. So if you put z equals 1, so then f of 1 equals 1 by 0, which is nothing but infinite. So for z equals 1, this function 1 by z minus 1 is becoming infinite. So this point z equals 1 is a singular point of f of z. So singular point is a point at which the function is not analytic, because here the function is becoming infinite at the point z equals 1. Now let us take one more example. So f of z equals e power z by z plus 2 into z plus I. So if you see the second example, in the denominator there are two linear factors, that is z plus 2 and z plus I. So we can say clearly that by seeing this function, so the function f of z becomes infinite at z equals minus 2, that is minus 2 plus 2 becomes 0, so 1 by 0 is infinite, and also at z equals minus I, that is minus I plus I is 0. So again 1 by 0 is infinite. So at z equals minus 2 and z equals minus I, the function becomes infinite. So z equals minus 2 and z equals minus I are singular points. And there can be more than one singular points for the function. Now let us solve some problems on Cauchy's theorem and Cauchy's integral formula. So before going to the problems, let us once again understand the statement of Cauchy's theorem, because we are going to implement this to solve the problems. So now the Cauchy's theorem states that if a complex function f of z is analytic on and inside a simple closed curve C, then the value of that integral, that is integral f of z dz over a closed curve C, is always equal to 0. That is by drawing the figure, if you take any closed curve C, if the function f of z is analytic at each and every points which lies on the curve C, and also at the points which lies inside the curve C, then the value of this integral f of z dz is always 0. Now let us solve the problem. Evaluate integral z square by z minus 1 dz over a closed curve C, where C is a circle mod z equals 1 by 2. So if you try to solve this problem directly, it is very difficult to solve. So it is better to apply Cauchy's theorem so that the simplification will become easy. So here you have to observe that we have to find the value of this integral along the closed curve C. But what is the closed curve C here? So the closed curve C is a circle mod z equals 1 by 2. So here, so the given function f of z is z square by z minus 1. So by seeing this function, we can easily identify the singular point. So now if you see the denominator here, z minus 1 is a linear factor. So it is clearly visible that z equals 1 is a singular point. So why it is a singular point? So when you put z equals 1, this function becomes infinite. So z equals 1 is a singular point of the function f of z. Now the given closed curve C is a circle, that is mod z equals 1 by 2. So if you put z equals x plus iy, so modulus x plus iy is equal to 1 by 2. So modulus x plus iy is nothing but square root of x square plus y square equals 1 by 2. So removing the square root, so x square plus y square equals 1 by 2 whole square. So what is this equation represents? So this equation represents a circle with center as the origin, that is 0, 0, and radius is 1 by 2. So it is in the form of x square plus y square equals r square. So this circle, that is mod z equals 1 by 2 or x square plus y square equals r square. So this equation represents a circle with center 0, 0, and radius is 1 by 2. The radius of this circle is 1 by 2. Now, so after writing the circle, now we have to identify whether this singular point z equals 1 lies inside the circle or outside the circle. So if you see the circle, the point on the x-axis is 1 by 2 comma 0. So x-axis is the real axis, y-axis is the imaginary axis. So the point on the x-axis is 1 by 2 comma 0, and the left side it is minus 1 by 2 comma 0. The point on the y-axis is 0 comma 1 by 2, it's an imaginary axis, and here it is 0 comma minus 1 by 2. So now we have to check whether this singular point z equals 1 lies inside the circle or outside the circle. So if you take z equals 1, so z equals 1 means it is nothing but 1 comma 0. So 1 comma 0, it lies somewhere here. So this is z equals 1. Z equals 1 or 1 comma 0. So the point z equals 1, it lies outside the circle. So what it implies, since the singular point lies outside the circle, it implies that the function f of z is analytic. The function f of z, what is the function given here, f of z? That is z square by z minus 1. So this function is analytic at each and every points on the circle, and as well as the points which lies inside the circle. So here you have to understand the Cauchy's theorems clearly. You are implementing the Cauchy's theorem here. Since z equals 1, the singular point lies outside the circle, the function f of z, it is analytic at each and every point which lies on the circle, and as well as at the points which lies inside the circle. So therefore, by Cauchy's theorem, so you can write, since z equals 1 lies outside the circle, f of z is analytic at each and every points on the circle and inside the circle. See, therefore, by Cauchy's theorem, integral f of z dz over c equals 0. Therefore, so what is f of z here? That is z square by z minus 1 over c dz is 0. Now evaluate integral e power z by z plus 2i into z minus 2 dz over closed curve c, where c is mod z equals 1. So now here f of z is e power z by z plus 2i into z minus 2. So if you see the denominator here, there are two linear factors, z plus 2i and z minus 2. So by seeing the denominator, we have z equals minus 2i. So if you take z equals minus 2i plus 2i is 0. So 1 by 0 is infinity. And again, if you take z equals 2 also, 2 minus 2 becomes 0. So again 1 by 0 is infinity. So the singular points are z equals minus 2i and z equals 2 are the singular points. So now we have to check whether these two singular points lies inside the curve or outside this curve. So what is the curve given here? So it is a circle, that is the curve C is the circle mod z equals 1. So mod z equals 1 represents a circle. So this is a circle. So center is 0, 0 and radius r is 1. So now draw the circle. So this is the circle, mod z equals 1. So the point on the x-axis is 1 comma 0, and to the left side it is minus 1 comma 0. On the y-axis 0 comma 1, and in the negative side it is 0 comma minus 1. So now, so z equals minus 2i means, so z equals minus 2i means it is imaginary number. So it is nothing but 0 comma minus 2. So where 0 comma minus 2 lies? So it lies somewhere on the y-axis. So this is 0 comma minus 2, and if you take another point, that is z equals 2. So z equals plus 2 means 2 comma 0. It lies on the x-axis. So this is 2 comma 0. So both these points, so that is z equals minus 2i, that is 0 comma minus 2, and z equals 2, that is 2 comma 0, both lies outside the circle. So both the singular points, so both the singular points lies outside the circle. So by Cauchy's theorem, the function, given function f of z, so it is analytic at each and every points which lies on the circle, and also at the points which lies inside the circle. So by Cauchy's theorem, integral f of z dz over c is 0. So therefore integral f of z is e power z by z plus 2i into z minus 2 dz is 0. So the value of this integral is 0.